we have looked into n-gram language models as well as RNN based language models. Now it is a new trend in NLP where people are using the transformers. So let's have a closer look at transformers. And let's start with what was wrong with RNNs. Like the you have seen in RNNs, what happened was like the sequence is fed into the system, or the RNNs one after the other. Like if you have a sentence of length 5, then the first word will go in, and then the second, third, and fourth. So it's sequentially processed. And if it's a sequentially processing, like you are depending on uh, the previous words to be there in the system and being transformed into some hidden state, and which hidden state is being again used again, then it's like you can't parallelize these computations. Like there is a dependency on the previous sequence. And then people also started using the attention mechanism, which we haven't discussed yet, but let's uh, understand, like the let's have a keep in mind like the let's give me a brief intro of the attention mechanism. What happens in attention mechanism is like you can focus on a certain words in the wherever in the sequence while processing one of the words, and it kind of a random access, like it's not a sequential access. And people were using this attention mechanism along with the RNNs, and then people were started thinking like why we need an RNN, like the sequential processing, if the attention can focus to any of the previous states or the upcoming states in the sequence, why we need an sequential processing. So then came this transformer idea. And as an overview, like the transformer is used in the task like the sequence to sequence transformation. Like in machine translation, your input sentence is a sequence or a string of words, and that's being transformed to a string of words in another language. So it's a sequence to sequence transformation. And it has an architecture like there is an encoder and then a decoder. So it encodes the input sequence to some vector format, then this vector format is decoded to the other sequence. And in translation, it's the problem is to predict each translated word, like the each word translated word at a given position. And usually people use cost and error function, cross entropy on the final layer. And this is the paper which introduced the transformer to the world. It's called Attention is All You Need. And it's uh, a paper came out of the research happened at Google Brain and Google Research. And you see like the how the different authors have contributed to the paper. Like it's a teamwork and everyone has substantially contributed. Then even the transformer is somewhat like the complex thing with multiple subsystems involved. So we'll have a closer look and see what all different things are there in the transformer. And here you can see like the uh, one submodule or the one unit of the transformer, like the encoder part and the decoder part, and what all different modules are there. And we'll see everything in detail. uh, am I still audible?
Yes.
Yes.
So as a black box, you can see like the transformer transforms one input sentence in one language to another. So it's a, I mean, any sequence to sequence transformation task can be solved using the transformer. And let's see like what's inside this black box. And as we said earlier, like there are encoders which encodes this input sequence into one particular vector format, and then there are decoder which takes in this encoded vector and convert to the output sequence. And if we look closer, like you will see like in paper they have proposed six encoder modules in sequence at the encoder side, and six decoder modules in at the decoder side. And there's no, I mean, it's not something magical about using the number six. Like people experiment with the different numbers, but in paper they have proposed using six encoder and six decoder sequences. And let's see like what all different things are there in the encoder and decoder modules. Like the one encoder module contains a self-attention module and a feed-forward neural network, the regular uh, neural network, like the similar to the perceptron. And decoder side, you have self-attention and feed-forward, and in between there is an encoder-decoder attention. And let's have a look at these different modules. So first, what happens is like you have a you have this sequence, like the word sequence, uh, and this needs for to be processed in the computer. This needs to be a number. So each word needs to be converted to a vector, and in paper they have proposed like the vector size of 512, like you will have a 512 length vector representing each of the words in the sequence, and which is being I mean given by the uh, initial embedding layer. So you may know like the what happens in a one hot encoder. Like you will have a vector size of which is of length, the vocabulary size of the language, or the vocabulary size of the uh, corpus you have used to train your model. And then you will have certain positions for each of the words where whenever it's one, then you say like that word corresponding to that position is using this. People use is like using an embedding layer in which the our training the system itself gives a some fixed length vector to represent each of the vectors, or sorry, each of the words. And once the words are converted to the vector, it's been fed to the self attention, and then uh, you get uh, some output out of it, and then which is being again fed to feed forward neural networks. And self attention, if you look at like why we need a self attention, like consider this sentence: the animal didn't cross the street because it was too tired. So there is this word it, and uh, what is the it? What thing in the other, I mean the other part of the sentence it referring to, like whether it's the street or whether it's the animal. To see that, you need to have some focus on the particular word which is referring to it. So in attention mechanism, what it happens, like you can see in the right hand side in this picture, like it has some focus parts, like these are the attention weights, and the animal has more weight. That's why the thickness of line connecting it and the animal is shown thicker compared to others. And so while encoding it at the encoder side, it takes uh, the input, the gives focus more on the animal part, like the weight for this animal part is more while encoding it. That's the idea behind using the self attention. And this self attention is learned, like the attention weights are learned through while the training is happening. So the system knows, like after training on a good amount of sentences multiple times, the system knows like where to focus when such a sequence has come. And let's have a look at the how the self-attention is implemented. So the sentence with two words, thinking machines, and you have this vector representation of thinking and machines, x1 and x2. And there are three types of vectors, which is required for implementing this self-attention mechanism. It's called queries, keys, and values. The terminology comes from usual information retrieval tasks like the search engines and all. You will have a query and you match it with the keys and you retrieve the values associated with the keys. And so in basic information retrieval case where you are doing word matching, like you will have a query like where is say like where is Taj Mahal, have the words and you split the words and then you match the words with the say documents subject of a document, like the title of a document, like where if whatever keys or the whatever titles give the good amount of match, like uh, which gives the maximum number of word matching, you retrieve that particular document, which is the value. So that this terminology comes from the information retrieval task, like queries, keys, and values. And you have certain matrices, weight matrices, WQ, WK, and WV, which transforms this embedding vectors to Q, K, and V. So you, what you do is like then you convert these embedding vectors to queries, keys, and values, and you multiply for if you are encoding the thinking, then you multiply the q1, which is the query of this particular word, to the keys of all the words in the sequence, and you get these numbers, like you got 112 here and you got 96 here, and you do one again a normalization, like you divide it with the square root of the dimension of this keys. Usually what happens is like the queries, keys, and values will be of dimension less than the embeddings. Like in paper, they have proposed to use 64 length query, key, and values vectors, and embedding is of 512 length. And this picture, it's shown like 4 and 3. And on that result you apply softmax so that it becomes something like a probability distribution, like something which add up to 1 and which is positive number and between 0 and 1. So you get these numbers, and that's your weight, like the weight of each of the attention weights, each of the words with this attention weight. Like v1 has this weight of uh, 0.88, then you multiply 0.88 with the v1, and for v2 you have a weight of 0.12. The it says like you need to pay more attention to the thinking while doing the thinking encoding, and very less attention to the machines. So then you get this z1, which is your um, final output to the feed forward network. Like you multiply this v1 and v2 with these values and add them up, and you get z1, and you do it for every position in the sequence. And so the whole process of vector multiplication and addition can be um, uh, done using the matrix operation. So you can just um, you can stack up the your embedding vectors for that particular sequence to be encoded, and multiplied with the this WQ matrix, and you transform the whole thing, like you will be multiplying the first row with the first column and uh, producing a value here, then the first row and second column and producing a value here. So usual matrix multiplication, and you get the same results as a batch or stacked thing. Like you will have queries for uh, all the embeddings and keys for all the embeddings and values for all the embeddings. Then you do this multiplication operation with query and the key matrix, and normalization with the root of the dimension, and multiplied with the values, and you get the z vector with all the z values stacked one on top of the other. And they have proposed, like, if they didn't stop at having one attention head, like they uh, propose to have multiple attention heads. So you will have multiple W, Q, WK, and WV matrices randomly initialized, and you will have, it's like you are when you want to make a decision or something, you will ask multiple people. Or in machine learning, in classification, you will, the ensemble methods, in which you will have multiple classifiers, and you take uh, the maximum, you take the uh, um, classification produced by most of the classifiers in that ensemble. The same way, you'll have multiple attention heads, so that one attention head don't make any mistake. And say there are 8 attention head, then you will have 8 such values, uh, 8 such C values out of it. And what you do is, like, you concatenate these attention heads outputs and multiply with a weight matrix, which is again the parameter of the model. Like then you take the output and feed it to the feed forward neural network. And this would be the out, output of our out of this multi-head attention. Like you have 8 different attention heads depicted by these colors, and then, like, you see, like, the four, while the it is being encoded, you see, like, the system is giving more, once it's trained, it's giving more attention to the animal and the tired, and some good attention to the street. So it automatically learns, like, after a while, training on a good number of sentences over and over, like it learns, like, where to pay attention while encoding it. And now one more thing which was missing, and in the RNN was this RNN is position encoding. Like in RNN, like how the sequence is, like, because you are feeding one after the other, and some information about the sequence ordering is captured there. So that sequence of this. So that's the place where this position encoding part is used. So what's the idea is, like, you have embeddings, and then you have certain vectors of the same length, which indicates the position of that particular word in the sequence, and you add those things and create a final vector, which is being then fed to the uh, other modules. So it will be like the position coding for first uh, position, you have this vector like 0011. Then for the second position, you have this vector like 0.84, 0.0001, 0.4541, and so on. Like for each position, there will be a characteristic vector, and you add that with the uh, vector embedding for that word coming at that position. And so they have proposed functions which generate these position encoding vectors. Like there are two sinusoidal functions they have proposed in the paper, and if you visualize it with a color and color coding, like it varies, the numbers varies between -1 and +1, and the based on the values you can see like how this heat map is being generated. For this is for a sentence length of 20, like the 20 positions are being depicted, and on the right hand side is some similar function um, depicted for positions, token positions 0 to 10, and this is how the position encoding looks like. And another idea which comes into this transformer is like as you are feeding the inputs to one of the systems, one of the modules, and you take the output from that module and so on, then some information is lost in between. So to re-add that information, like you take the residual connections, like you skip that module. Like here you can see like the self-attention module is some the information is going through the self-attention module, as well as there is a residual connection which is a dotted line, like you are feeding that inputs directly to the upcoming uh, modules as well. And in this you see like the right after the self attention you have this add and normalize. And what happens in this is like you you have an output, like I'll explain it here, like you have an embedding with position encoding added, and you fed to the self attention and you get these z vectors, and then what you do is like with the residual connections coming in, that residuals like these x values are added with these z values coming here, and you perform a layer normalization. In layer normalization, what happens is like you uh, uh, subtract the mean of this, whatever the values there, all the values from each of the rows, and you divide it with the um, standard deviation of these values, these rows. Then the whole thing is somewhat normalized, and it just captures like how much the things are differing from the mean value. Like you won't be having a very large values, very low values and all, like it will be all normalized. So every stage there will be this layer normalization happening, and once the output from that is then again fed to the feed forward neural networks, and again add a normalization. That's how the encoder part is like. Here you can see like two encoder modules and two decoder modules, and then the final the linear layer and the softmax layer, so all depicted together. And you can see like the from the final encoder layer there is this connection going to this encoder decoder attention layer of this decoder module. And this encoder decoder attention is similar to the self attention. What happens is like it, while decoding, it looks for what all sequences in the input needs to be focused on, other than the sequence it's processing. So you decoding process, like the at one time step one, decoding for the time step one is happening here, and the output is one. And what happens is like you fed this sequence to this encoder part, and then encoder is connected to the decoder through this encoder decoder attention mechanism, and then at the output you are supposed to get this uh, value or the word corresponding to the position for or the time step one. And let's have a look at the final software layer in this decoder part. So you get some output of this whole decoder stack, and that's being fed to a linear layer, linear feed forward neural network, and you get these logits or the numbers which may be positive, negative, very large values or something. Then of the this whole vector would be of the size of your vocabulary, and then you apply a softmax layer. Then you transform this into a something like a probability distribution which adds up to one, and values between 0 and 1, and you figure out which of these values is the maximum in this whole vocabulary or the whole uh, vector, and that would be the output for that particular time step. Like here you see like uh, the position 5 is the maximum value, and uh, for that position 5 corresponding word is am. So let's also have a look at the how the training is being done in transformers. So you have, say, consider like your uh, whole corpus is having this many words and only like the five tokens end of the session. And if you are one hot encoding am, you are supposed to have a vector like this, like the am will be 1 and all others will be 0. That means that this whole vector represent the word am, and so this will be your uh, say, consider like you are starting your training process, like uh, your untrained model output is like this, like some random numbers, and your desired output is like you are supposed to have a thanks there, and your desired output is this thing like the 0000100, and now you have to identify like what's the error happening here, like how much it is differing from the uh, expected output, the current output, how much it is differing from the desired output. So like these are two probability distributions. Like to compare two probability distributions, you usually use the cross entropy laws, and use the once you calculate the cross entropy loss, you propagated error, and then change your parameters accordingly. All the attention weights, all the feed forward layer weights and biases. So everything is updated according to this final error, and your aim is to minimize this final error and adjust minimize the final error by adjusting all these parameters. And once the system is trained on large number of corpus, then you will have a properly set parameter things, and then subsequent decoding happens. And say like the usually like your probability distribution, output probability distribution is of vector of with vocabulary size, and say like of it would be like of the order of tens of thousands, and say like for you here you can see like the for 5 timestamps, the what would be the expected probability distribution going to be is showcased here. Like first timestamp, it's supposed to have an I there, and for second position it's supposed to have an am there, and for the third a, and so on. So you get an trained model output like this, like probably like you if your model has trained on a trained and having a good accuracy on the decoding task, like you will have some probability or distribution looking like this for the positions, like higher probabilities for 1 in the position 1, in the I for the position 1, and for the position 2 it's for the am, and so on. Like you have the similar kind of probability distribution. And that's all about the training of the transformer. So it concludes the overview of the entire transformer architecture. And you may also go through this paper. Attention is all you need. And there are many explanatory resources which I'll post it in the group. It's the channel itself, which you can quickly go through and understand the further details of the transformers. So any queries, any questions, any doubts? Hello.
No.
So you're clear with all the things here, or is it too complex to comprehend in one go?
Yeah, like it's a bit complex. But yeah, like it's somewhat understandable.
If you look at the whole thing, like the main idea is like based on the where to focus on while encoding as well as while decoding, and you have
That's where the
parameter.
attention part comes.
Yeah,
Yeah.
you have the whole parameter matrices which captures this information. Like the numbers in those matrices will change over time while the training process is happening, and then you it has that much degree of freedom to incorporate all the attentions for the whole common sequences in that language. So if you look at the GPTs, the newly released GPT-3 and all, like this, the parameter size is something of the order of just millions, right? Parameters, like it's a very huge number. Like its models are also like big GBs of size. Like all this attention weights as well as the feed forward networks, weights and biases. In the upcoming sessions, we can look at how this thing is being used in training the language models. Like the transformer idea of transformer has kind of said as the image net moment for what you call NLP, because it enabled the people to use the pre-trained models and do transfer learning on top of that. Like you will have a very large model trained on a very large amount of data, and you have some domain to be applied, domain in which uh, you need to apply this model. Then you have a very small corpus from that domain, and you do a transfer learning on top of this pre-trained model, and then you gain a good accuracy. And recently, performers like the transformers are known to have too much complexity, like exponential complexity over the the corresponding to the length of the sequence. Then this in terms of the computation, then this something which scales linearly has come, which is called performers. Like we can also look into that in later. Okay. Okay, so don't have any queries. Uh, Thank you so much for your time, and I'll post the other resources in the channel. So, okay, bye bye.
Thank
Have a
you.
great day.
Bye.
Thank you.